just in case anybody misses it and wants to see it later, okay? And so this is going to go onto here, and we are going to do, because it is carbon dioxide, it is not soluble in water, so we can collect it over water. So we're going to collect it over water. So what I'm going to do is I'm going to take, I have a little tub of water over here, behind here, and this is going to go into here, but I'm going to use a stand and clamp. And some of you won't have used a stand and clamp, so I'm just going to show you very quickly. Go on to the other camera. A stand and clamp is a way of holding the chemicals which we want. Okay, I'm just going to move away a bit. So the stand is a long metal pole with a base here, and normally it will attach the clamp, which will look something like this, not necessarily this color, and it may be just two holes, it doesn't matter. But this needs to attach to this with one of these, okay? So if you're given this in the pieces, you may be given it assembled, but if not, assemble it. So there are two screws, this one, doesn't matter which one, they're identical. So we just slide them onto it and screw it up, and that will stop it sliding down. And then the clamp goes into the other one, okay? Now the clamp, in general, has one arm that moves and one that doesn't, okay? So this one doesn't move. So if I hold this one and I wind the clamp, you'll see that the other one moves and this one doesn't, so it closes down on it, okay? So I put this in here, and now it can clamp something vertically, so it could clamp, let's say I'm going to clamp this would be a bit silly. No, I will clamp a boiling tube, okay? If I clamp this, I can just turn it over if I want it to be horizontal or at an angle and so on. So they're very useful, but sometimes you get these in an examination and then they don't show you how to use them. So I just thought I'd show you that there. Okay, so I now have over here, and I'm going to zoom in a bit. I now have the conical flask, cone-shaped, the delivery tube, and I'm going to collect it over water, so I need to fill up a measuring cylinder that is going to collect the gas, and I'm going to put it into the water. To do that, I have to fill up the measuring cylinder completely with water. I'll just go back a little bit, it's a bit too close. So I've filled this up with water. I now need to turn it upside down in that. They may give you a cork to put in here, but it's easy just to put your hand on top, turn it upside down, put it inside, and the water won't come out. I'm going to clamp this like this, so the water can't drop out and I don't have to hold it anymore. Now, if they don't give you a clamp, sometimes you just have to hold this, that's okay. You can lean it over because it won't make much difference. So then it says, measure out, and I have here some hydrochloric acid that they're asking me to measure out. Measure out 50 cubic centimeters, 50 mils, 50 cubic centimeters of acid. Now, to measure that out, you would normally measure in a measuring cylinder. A measuring cylinder, and Genesis and I were talking about this earlier, a measuring cylinder is not very precise. It is not very precise. But it's quite good if it says measure out 50 and it doesn't say it's got to be exact. So we just pour it in, no problem. If we pour a little bit too much in, it doesn't matter, we can take it out again. But one of the most important things is knowing that when you measure something out, it should be the bottom of the meniscus, the curve of the liquid, it should be the bottom of the meniscus on the line, okay? So I've got this. So I'm now going to put it into my flask, and I'm going to tell you why I think this is the best way round. So what I'm going to do is I've got the acid in here, I've got my powder in this, I have the delivery tube, which is going to go underneath here. Okay, so I'm going to sort that out first so it's all ready to go. Just going to lift this up a little bit. Okay, so that's all ready. Now what I want to do is I need to get the powder in and collect all the gas. Now that's quite difficult. So what you've got to do is you've got to get ready by taking this out, get your powder ready to go in, and that means taking the powder and tapping it all down to one end so you can get it all to go in really quickly, okay? And then I'm going to tip it in and put the top on really quickly, because otherwise I'm going to lose most of the gas, okay? So I'm going to chuck it in, put the top on. And you can see the gas going up here. And the reaction is over. This is the problem with this sort of thing. The reaction is over really fast. And because it is over really fast, we have to make sure that firstly, almost all of the powder went in, and secondly, that we got the top on quickly enough to catch most of the gas. Now, two things happen. Firstly, you can probably see in here, there is still some powder. So I could weigh that and I could find out how much I did not use. Okay, that's quite good, because if it says add 0.3 grams and I weigh out 0.3, but then I don't use it all, I need to write down, oh, I only used 0.27. Okay, that's important. The second thing is that I missed some of the gas, and I need to write that down if I'm going to analyze the errors and so on. If I'm going to say where my reaction might have gone wrong, then I'm going to say, I know that quite a lot of the gas went out. All right, so here we are. So it produced almost exactly 30 cubic centimeters of gas, okay? All right. Now I'm going to weigh the little bit of powder that I've left, but to start with, I'm going to show you the calculation. So I know, let's go up a little bit. So I know this was a metal, group 2 metal carbonate, okay? And I reacted it with hydrochloric acid. And it reacts, acid and carbonate makes calcium chloride and water and carbon dioxide. I think you can probably balance it very easily. Anybody call out, how do I balance this? Having a look at this. You have a look at it while I just weigh out the amount that I've used here. I'm just weighing. Okay.
You put 2 in hydrochloric acid.
Absolutely right. So I need 2 of the HCl's. Okay, so if they say write the balanced equation, there it is, easy. I'm sure most of you could do that. Now, I know that I got, let me just check. Oh no, it's 32 cubic centimeters. I got 32 cubic centimeters of the gas. Now, I'm telling you that I know that this was in excess. So in other words, all of the MCO3 has reacted. I have just weighed it and I found that I only actually used 0.22 grams because some was left in there, okay? It wasn't 0.3, it was 0.22. That's okay. It doesn't matter that I didn't use all of it. That's not really important. So, what I'm going to ask you to do now is, while I get ready for the next experiment, hang on. Let me
Excuse, I have a question.
Hang on. What I'm going to ask you to do is to work out what M is, okay?
I have a question.
Hang on just a minute, Silver Spring. So there's one piece of information which they would give you in the question, which is 1 mole of gas occupies 24,000 cubic centimeters, okay, at this on a day like this. In here it is quite warm. Today it is 24,000 cubic centimeters. I will write it up on the board in a minute. So while I just clear this away, what I want you to do is to try to work out this, because this is, so the skills here, and we will go through them again, were about weighing carefully, weighing before and after to find out how much we used, how much we actually used. They say use 0.3. I didn't use 0.3. I had excess acid. I don't have to worry about that. I had to put the top back in really quickly, and I know some gas escaped, but I can't do anything about that. Some people sometimes have made a little container for the powder and floated it like a little boat and float it on the acid, put the top in, and then shake it, and it mixes them. That's good. That's a very good technique. If you get this sort of practical, it's something you can do. Measure the gas as closely as you can. I have, and then do the calculation. So the other piece of information which I will put on the board just now is the mole of gas. So what I want you to do is start with the moles of gas, realize that there are the same number of moles of carbon dioxide as there are of MCO3, and see if you can work out what M is, okay? So here's the board, and 1 mole of gas is 24,000 cubic centimeters. Have a go. Just have a few minutes and see whether you can work out, even if you don't have a calculator, just see if you can work out how to do the calculation while I get some chemicals ready for the second one, okay?
Excuse me, Mr. Ma'am.
Hello.
Excuse me.
Hello.
We are calculating the mole of the carbon dioxide.
We are trying to find the RMM, the molar mass of MCO3, and therefore what MCO3 is. In other words, it is a group 2 carbonate. Is it magnesium, calcium, barium? What is it? Okay. So we want to try to work out the RMM of MCO3. We know what CO3 weighs. That's easy. So what we want to do then is to take that away and find what M is. What is M? Okay. We'll come back to it in just a minute. I promise. How is it going? Are we okay? Does anybody, please do not call out the answer if you have worked it out. Just if you have done it, just show me a thumbs up so I know that you are doing, it will be extraordinarily well if you have done that. Wow, hey, very, very good. Well done. Excellent. We'll give some others just a moment longer.
But you've already give us the elements.
I haven't told you what M is.
But
I'm
in
asking
your,
you what
In
I'm
your
asking you
equation,
what M is.
just give us. In
In
your
your
equation,
in your equation, the
Products.
product of the reactants, there is no symbol of M.
is calcium.
You've omitted the M.
Oh, sorry, I just wrote Ca. Sorry. Sorry, I didn't, I meant to, I was just thinking of a group 2 metal. My apologies. I was being silly. I was just thinking of a group 2 metal because earlier, when I was weighing out something else, I used calcium carbonate. My apologies. I didn't mean to write that. I meant to write M. So it could be calcium, it could be magnesium. Obviously, it could be, it's unlikely to be barium because barium carbonate is very toxic. So I don't think I would use that. Sorry about that. Okay, are we done? Are we done? Yes. Okay. Let's come back and see what's happening. Okay. So who can tell me what M is? Is M Ca? Is it Mg? Is it strontium? Is it barium? I don't think it'll be radium. Anybody got an answer? Who can tell me? Is there anybody in Socorro Girls who can tell me what I do?
Yeah.
It's calcium.
You think it's calcium? Can you tell me how you did that, please? Come on, Silver Spring, Samuel. Come on, be courageous. Come on. Tell us how you did it. Come on.
It was just a trial.
What?
It was just a trial.
You broke up there. Luckily for other people. Okay, so what we do, here we go. Here we go, very simple. Most of you will have got it, which I'm very pleased about. So in other words, we go like this. Okay, the moles of carbon dioxide. Moles of carbon dioxide is very simply. So I work out the moles there, and I work out the moles, and if I take 3 over 24, 32 divided 24,000 is, and I would always leave the answer on the calculator. So whatever it says on your calculator to start with, you don't change it, all right? Don't approximate at this point. Don't ever approximate until the end, okay? So this is 0.0013 we're going, okay? And that will be the same as over here, 0.0013. Now, RMM from the triangle, for those of you who remember, and when we were doing moles, go up a little bit. Moles, RAM, underground, for those of you who were here when we were doing that. And therefore, if I want to find this, I just want my grams over my moles, so I want that. So it's 0.22 divided by 0.0013, which comes out as something like 169. Is that right? Is that right? Is that right? Good, come on then, come on, wake. Ushirika are really on, which is good. Immediately they spotted where I had written something down wrong. It's very important that we notice our calculations. It is very unlikely that that's correct. So what's gone wrong? Ushirika, do you want to explain? No? Anybody? Is this okay? $160 what? $169? Did we get 169? Okay, Genesis got 169. Okay, if it's 169, what do we do next? If it's 169,
65.
what do I do? This is for MCO3. So what I have to do is I have to work out the mass of this. What is the mass of this? What is the mass of CO3? Anybody?
60.
60.
It
Right.
is 60.
So if that's 60 and the whole thing weighs 169, then M must weigh 109. Yes? Which group 2 element is closest to 109? Which group 2 element is closest to 109?
Pardon?
It is barium. So what has gone wrong? Because it has not come out at 137, which is barium. It has not come out at strontium, which is a lot less. So what has gone wrong? Does anybody know what has gone wrong? It's very important that you're able to talk about what has gone wrong. Anybody? It, 165 doesn't make any difference, does it? It is 165. It doesn't make any difference. The point is, when you have done this, you have to explain what has gone wrong, because it is not coming out as exactly one of these metals. And that's right, that will happen. One of the reasons it happens is because the MCO3 is not pure. Almost any group 2 carbonate is not pure MCO3. It's MCO3, MOH2, okay? There's a lot of different things in there. Yeah, I know it's 165. Thank you. But 165 doesn't help. Yes, thank you, Glory. Thank you, Glory. Well done. It's 165, not 169. That's not the point. This has not come out as any exact metal. So the next question is, what could have gone wrong? Where is the error? And there are 2 sources of error, and you should know these. One, and I pointed this out, putting the powder in and putting the top on is very difficult. Without any escape of gas, it's almost impossible. So that is important. And the second thing is, and it is always true, that the metal carbonate is not pure. So those are your 2 answers. So if they say, explain why it doesn't come out exact, then you have to say that. Okay, next experiment. Next experiment is a titration. Most of you will know a titration. A titration uses a burette and pipette. So, this most of you will know, I think, as a burette. This is a wooden stand. It might be a metal stand like we had before, it doesn't matter. When you come to these, this is off, this is on. They are very delicate and very expensive, so you have to be very careful with them. You may find that you have a different kind of tap. That is not important. In this experiment, I'm going to be asked to do something special, okay? And one of the things you are often asked to do is to make up a solution of a particular chemical. And in this experiment, they have asked you to make up a solution in a volumetric flask. This is a volumetric flask. A volumetric flask has a small line on it, and when you make up the solution in this, you must be very careful to add the water, whether it is with a pipette or a bottle like this, that it only just comes to the limit. Okay, that is really, really important. What is really important second is that when we have done this, we shake it many, many, many times to make sure it is completely mixed. So this is a very common experiment they ask you to do. They're asking you to, sorry, let me just change this. They're asking you to make up the solution. So you weigh it out carefully, put it into here, small amount of water, shake it, get it to mix properly, dissolve properly, and then add the water up to the little mark, and then mix it many, many times, okay? I'm not going to do it today because it's boring, but that's what we do. We normally say, turn it over 20 times, okay? That will make sure it's properly mixed. Then it says, fill up the burette. This is an acid, okay? And this is going to be an acid which is H2X, okay? H2X. I'll tell you more about that in just a moment. Then it says fill up the burette. So let's look at the burette. Let's fill up the burette. Now, if I'm asked to add something like sodium hydroxide to a burette, I have to be careful about how I do it. So I have to be very careful. Oh, come on, focus. Careful about how I do it. So I would normally use a small beaker. I would pour it in very carefully. I have to make sure that the tap is closed at the bottom. Some of my students, when they forget to close the tap at the bottom, so if you don't have this closed, you can spend a lot of time trying to fill up the top because it keeps on going out. I've had my students pouring it in the top, but it's coming out the bottom, and they're saying, hey, it doesn't fill up. Stupid. Okay, so turn off the tap. Fill it up slowly at the top. Carefully, very, very slowly, because we don't want it to overflow. And we're going to fill it up past the zero. The zero is at the top. I'm going past the zero because afterwards I want to let some out of the tap, because there is a small air bubble here in the tap, and I have to get rid of this, okay? I have to get rid of this little air bubble. So I turn the tap on and fill up this liquid, okay? Then I look at the top and I let out a little bit at the top just to get it down to the line, okay? All right, so this is now ready to be used. Then I have to pipette. This is a pipette. Pipette fillers come in many different types. Sometimes you're asked to mouth pipette. This is not a good idea. It's really not a good idea. There are many different kinds of ways of filling it up. Lots of different ways of doing it. I'll just show you with this one. These ones, you evacuate this first. So this empties, it goes flat, and then it fills up again. That's easy. These ones are not so easy to use. So you put the end on here like this. Don't push too hard. You don't want to snap the glass off in your hand, okay? And then this thumb, let me just take it off and I'll show you. This goes up, okay? And that sucks the liquid up. Okay, so let me show you. Here we go. So I'm now going to pipette out. I haven't got a conical flask. Just one moment, sorry. I would get a conical flask ready. I would always get it really close to it, really close to the solution. I put this in. I don't go down to the bottom because otherwise I'm trying to suck the bottom of the glass up. That's stupid, so I hold it up. And then if I just angle it up a bit, you'll be able to see. As I move this, the liquid will go up. You will see it inside, it is going up, okay? Hopefully you can see it is going up inside, up in here. And there is a little line just here. and I have to get it onto that. So I will, sometimes it takes a little while to get it right, oh, gone below, etc., etc. So I'm not going to bother doing that exactly today because I want to get on. I take it out, I put it into here, and I either just take this off, is the easiest way, and then the liquid will come out. Don't let go of this because it will fall over, you will have to do it again, okay? So I have now the liquid in here. Now so what I have done is I made up a solution. They often say, make up a solution of the chemical. So you put it in here, mix, make sure it's on the line, be exact. Pipette, 25 cubic centimeters is what I've got here, into a conical flask. And then I add an indicator. Now often they will tell you what the indicator has to be. It is very often this one, methyl orange, or this one, phenolphthalein. You may have come across these. Make sure you know the color change. So I'm going to add this methyl orange. I don't add too much, so I add just enough to color it. That's 4 drops. That's enough. Then I put it underneath the bottom of the burette. Okay, so it's underneath the bottom of the burette. Let's get a little bit closer. All right. So now what I do is I turn this on, and the very first time I do it, I do not try to be accurate. I don't bother. So when I'm doing it, I just turn it on, and as the alkali goes into the acid, nothing is happening. There is no change. There's no change. I might mix it. We should always mix it carefully to make sure the chemicals are getting together. I am not trying to be accurate. I'm just trying to see about where the end point is. Now, oh, aha! It has changed. I don't mind that I didn't get it exact. I want to know approximately. This is my first go, and I write it down. I'll show you what it says here. I'll show you where the limit is. Let's see if we can get it in focus. Not quite. It's a little bit higher. Can you get in focus with my hand, please, camera? Okay. So here's the liquid level here, you can see it. And what you have to do is to realize it's going 22, 23, 24, 25, 26. So it is between 25 and 26. Now, recording these is very important. Because this one was rough, I'm just going to call it 26. I don't care. But this one is actually, and sometimes it is good to hold a piece of paper behind it, sometimes a darker piece. You can see whether it's easier or more difficult with different colors of paper to see behind it. Here is a glasses case, maybe it's easier. That is a bit easier. So this is where this is measuring, and you need to take a moment to make sure. This is 25.7 and a little bit, okay? Now, we're not too worried about this particular one because I've got a set of measurements for you for something that I did before. I'm going to write them on the board and you're going to have a go at doing it. Let's just remember what we did though. 1, we close the tap on the burette. Okay, clamp it very carefully, close the tap, fill it up. Then I was asked to make up a solution, and I have to weigh out the amount of the solid, put it in here, put in a certain amount of liquid, shake until it is completely dissolved, and then I fill up with water very carefully, and then I turn it upside down several times, a number of different times. Then I use the pipette. I got the conical flask very close to the flask, so that I didn't have to carry it far. I might use one of these. Doesn't matter which one I use. If it's one of these, If it's one of these, you press number one. You press number one and empty the bulb, okay? And then when you hold number two, it sucks the liquid up, okay? All right. So I transfer it, a few drops of indicator, not too much. If you use too much indicator, it changes the pH. Indicators change the pH of the solution. Okay, so I don't want to use that. All right. So now I'm going to write on the board what the calculation is, and you can see if you can do it. So I had H2X. I'm going to try and find out what X is, okay? That's the idea. I'm going to try and find out what X is. H2X reacts with sodium hydroxide and it gives Na2X and water. You can work out how to balance it in just a moment. And I took 4.21 grams of this in 250 cubic centimeters. That's the HX, okay? And the sodium hydroxide was 0.400 moles per litre. And I measured out 25 cubic centimeters. Whoops, sorry, wrong one. This was in the burette. In the pipette, I measured out 25.0 cubic centimeters of this, okay? And the answers come out like this.
We cannot see the product side clearly.
Sorry?
Excuse?
Yes?
We cannot see the product side clearly.
Okay, is that the light?
Yes.
Yeah.
Okay, hang on, I'll just see if I can get it. I'll just turn the light off. Let's see if we can make that better. It should lighten up in a minute, hang on. This should get ready in just a minute, it should lighten. No, disaster. Again. No, it's disappeared. That's very good. That's really rubbish. Wow, that's really good. Let's see if we can come back on another camera. You know, you sometimes have very expensive camera and it's rubbish. So let's just move this one across. Now, you still may not be able to see it very well, but I think, is that a bit better? Okay, all right. So, I took 25 cubic centimeters of this, and this was the concentration in the burette, and the volumes which I used were, oh, and you should set up a little table like this. So from the burette, what we would normally do is we'd say the final volume, the start volume, and therefore what we call the titer, okay? So let me give you an example. In that example which I did there, the rough one, I started at 0 and I went to 25.7. So I take this away and it's 25.7. But I'm not going to use this one because this one was rough. So here are the real answers. Here's some one that I really did earlier. So you had some proper answers. Okay. So I took this and I actually went for 26, and it's 26.00. This was 49.24. So what was that? Then I filled it up again, so it starts at 0.00, 23.22, and 23.22, 47.20. Okay? So what we do is, first of all, what we do is we work out how much we've used. All right? So the idea, very simply, is that I write down what it started at and what it finished at. So my answers come out, I just subtract, okay? So I get 23.24 for this one, 23.22 for that one, and 23.98 for that one. Now I want to point out something to you, and this is very important. Firstly, you do not use your rough reading. Okay, that's why I've crossed it out. I don't use that one. So then I look at the other three, and I try to find at least two which are very close together. They should be within 0.2. Okay, preferably within 0.2. So that means 23.24, 23.22, 23.98, I am not going to use this one. Do you see that? The other two are very close together, but 23.98, I made a mistake. If I get three which are not close together, I keep on going until I get two which are very close together. Okay? It's very important we do that. So I then average these two. I find the mean of the two or three which are close together. All right? So it's 23.24, 23.22, it's 23.23. That's the mean. Okay, 23.23. So 23.23 cubic centimeters of sodium hydroxide. Okay, so these were my results, real results. 23.23 cubic centimeters of 0.400 mole per litre reacted with 25 of this. Okay, 25 of this. See if you can work out, firstly start here. So the way that you should work it out is the moles of NaOH to the moles of H2X in 25 to the moles of H2X in 250, and then I can work out the RMM. Okay? That's how I want you to try and do the calculation. That's the best way of doing it. While I just get ready with something else, I'd like you to try and do that calculation. Okay? Let's see if that camera is working again. Let's just see if it's working. Hang on. No, it still thinks it's night. That's very good. Welcome to night. In the UK, it's night now. Oh, no, it's not. Okay, so have a go at that while I sort out the next one. I take it you balanced the equation? Did you balance the equation? Somebody at Genesis has spotted it. So we need to balance the equation. So have we balanced the equation? Yes. Yes, Glory. So you have to be very careful with a gesture like that. In the UK, a gesture like this is not something that you do to a friend. This is okay. This is not. This means 2 or victory. This does not.
You put 2 in sodium hydroxide.
Yes.
Excuse me, Mr. Mark.
Yeah.
Yeah?
Nope.
No,
No?
no,
You sure?
Vanini.
yes.
Okay.
I'm sure.
Kwa kamera tunamashua.
Well, hey, I'm sure. I know. If you're sure it's not 2, then okay, it's not 2. We'll just see Genesis. We'll just see what Socorro and Silver Spring and Usharika and Glory say. Yeah, we'll just see. You did see. Oh, she has disappeared from camera now. She has disappeared from camera now because she's going, yes, no, I'm sure. I'm really sure. Yes. Am I? Ushirika, 1 or 2 waters? In this case, the water doesn't matter, but we need to balance the equation. Okay, so let's have a look at this. Moles of sodium hydroxide here. 2 to 1, so the moles of H2X are half as many. That's the amount in 25 cubic centimeters, what I measured with the pipette. I multiply by 10 here. I can then take the grams, 4.21, divide it by the moles, and it should tell me. Has anybody got an answer? Because I need to get on because I want to do the next experiment very quickly. Has anybody got an answer? I just want to see if the other camera is working because I need it in just a minute. No, it's still night time. You're a very stupid camera. Okay, let's just see. Hang on, I'm just going to see if I can play with it to make it lighter. Oh! Ah, magic. Look. Juju. Right. Okay, moles of sodium hydroxide, 23.23 divided by 1000 times 0.4. 23.23 divided by 1000 to turn it into litres times 0.4 is 9.292 times 10 to the minus 3, or 929. I then divide by 2 to work out the moles of H2X. Then I multiply by 10 here, because 25 out of 10, so I multiply by 10. And I get a number which here, the moles here, looks like 0.04646. that would mean here that it is 4.21 divided by 0.04646 comes out as 90.61. 90.61. 90.61. So if you have got 90.61, you've done very well. Okay, last little thing, very quickly, because I know it's time to go. I just want to show you one more experiment, very briefly. So I'm going to go down here. This is the other major experiment which they ask you to do. This is a very, very common one that they ask. It's about measuring heat energy. They ask you to measure out a certain amount of something like copper sulfate. They ask you to weigh out a certain amount of zinc and add them together. Okay, so let us assume that I have measured this accurately. I haven't. So here's my copper sulfate. Okay, so we will assume I have measured, let's say, 25 cubic centimeters. Okay, so I've got that in here. This is blue liquid. I am then going to take the temperature of it, and then I'm going to add a certain amount of zinc. So I'm going to weigh out my zinc. Here, I'm not really going to weigh it out, I'm just saying I have measured some out. So now I have my zinc and my copper sulfate. So what they ask you to do then is to measure the temperature every 30 seconds. Now, if you're going to do that, you have to start measuring the temperature before you add the zinc. This is really important, because sometimes the bottle of copper sulfate came from a warmer room, so we have to take the temperature every 30 seconds before we add the zinc. So I have time 0, 30 seconds, or half a minute, 1 minute, 1.5 minutes, 2 minutes, and on 2 minutes I add my zinc. This is really important. So I would be writing down on my piece of paper, I would write down a table, and in the table it says minutes and temperature in degrees Celsius. Okay, so I go half a minute, 1 minute, 1.5 minutes, 2 minutes, 2.5 minutes. It's quicker than writing it out in seconds, 3 and so on. And at 2 minutes, I would normally add the zinc. Now what you do next is very important, because it is very easy to get this wrong. Let's go to it. If what you do is you add the zinc and you just wait, it will be wrong. What you have to do is, I've been measuring the temperature very carefully. I now add the zinc and I stir continuously. It is very important, stir continuously. And I have a watch or something, and I just check, and at a certain time it is changing color. At a certain time I measure the temperature. Oh yes, it has gone up. It is now higher than it was. I don't know if you can see that. It is going up. But I must keep stirring. I must keep stirring, because that mixes the chemicals and helps them to react. Yes, look, it's much warmer now. It's 50 degrees. Okay, it is going up. It is going up inside. We can see it is definitely different now. So I am mixing it. Every 30 seconds, I measure the temperature. It's now up at 60 degrees. That's really quite good. That's quite warm. And I keep on keep on measuring and stirring until it starts to go down. Okay? So every 30 seconds until it starts to go round. Now I'm going to stop and I'm going to show you what the graph will look like, because they will ask you to plot a graph. Okay? So the graph will look like this. Change camera. So I will plot a graph which will have time along the bottom. Okay? Sorry. Time along the bottom. I know there's a bit of light on it. It doesn't matter. So this says time. I would write in seconds. Okay, so I go, okay, that's 30 and 60 and 90, 120 and so on. And at 120 I added the zinc. Up the side is temperature in degrees Celsius. Okay, now this one actually went up to about 65. Let's assume it went a bit further. I might make this 0 and this, let's say, 80, okay? So I'm hoping that I get a flat 4 like this. At this point, at this, I add, let's try this other camera, see if there's less glare. Sorry, I'll just try the other camera, see if there's less light off it. Yeah, that's a bit better. So at this point here, I've added the zinc and it will start to go up. So next 150 seconds, ooh, look, it's going up. Now, what happens is it goes up and then it starts to slow down and eventually it starts to go down. And what you have to do is you plot the line which goes like this and then it follows like this. What is really important is you realize this. If I get a straight line, do you want something? Are you okay? No fun. If I get, this is the rate at which it's cooling. So this is it cooling down. If I draw a line back here to this point here, that is the real temperature rise. So I've got it cooling here. I draw a line back here. And that is the line. If all of the heat had been given out at one time, then it would have gone to here. But it was cooling all the time. This is how we do it. So from here, so let's say this goes up to 85 or something. So it's from, let's say, 22 to 85, and that's how you do it. They will then give you a way of doing the calculation, which we can look at next time. Okay? Last bit. I said there was something to look at, and I was going to ask you a question about it, so here it is. I'm just going to focus on it. Okay, so do you remember I put some copper and some silver nitrate? So let's just see what it looks like now. Oh. What has happened? Anybody? Let's have a look at it a bit closer. What has happened to the copper? Anybody see? So the copper has disappeared. And we now have some very strange grey and shiny. What is it? Does anybody know what it is? It is juju. No, it's not. There's no juju in chemistry ever. It is a replacement reaction. The silver is less reactive than copper. And so the copper forces the silver to be displaced. So in other words, the copper is losing electrons to the silver. So the silver is gaining electrons, that's reduction, and the copper is losing electrons, that's oxidation. Okay? All right, that is recorded, all of it is recorded, so I hope some of that is useful. I will send the video to you. There is the very strange crystals. They are very strange. They really are. They're quite beautiful. If you shine light on them, they are quite shiny, but that's it. Okay, right guys, it's already 2:30, So I think probably you need to go. You have been very patient and I hope it was useful. When we do, in 2 weeks' time, we will do some more lab work, but it's quicker, much quicker. If you get a chance, have a quick look again. Just think about being precise in paper 3. It's very important, measuring things carefully and so on. But now it's time to go. So thank you very much for being there. And as Silver Spring likes to say,
Kuna
that
Matata.
says, if I can get the shine off it, that says sodium methanoate matata. Sodium methanoate matata.
Hakuna Matata.
Hakuna. Oh yeah. All right, guys. See you again. Okay, I'll see you next week. Next week, theory. Do ask your supervisors for the questions with the answers. Very nice to see you, Usharika. Lovely to see you, Silver Spring, Glory, Genesis. You're all great. Well done. Have a good evening. Thank you very much.
You too.
Cheers, Michael.
Thank you, Teacher Mark.
Thank you very much, Sophia. Michael, I love your top, Michael.
We hate you. Abdul.
Oh no. Here's the can we go through the survey process? Hi Dan, how's it going? Dan's looking a bit serious. Dan's going, I've had enough of this chemistry, I hate it. Whereas Fatma is going, yeah, give me more chemistry. I'm going to be a math teacher. Idiot. She got no brain. Anyway, are you okay, guys? Yeah?
Yeah, we are good.
Excellent. That is very good. Hey, my favorite 3 supervisors. Really, seriously, you guys, you 3 are just brilliant. I really, really mean it. You are so, so good with the students and with us. I love it. Oh, Dan's gone for a walk. Look, Dan's so tired. He's like, oh my God, it's been such a long day. Poor Dan. Dan has gone to run around outside like a small child.
Not really. It's been so interesting.
It's been what, sorry?
So interesting.
Oh, yeah. Well, it's very kind of you to say, Dan. Seriously, if you get a chance to show them those questions and answers, I don't know how easy it is to print out a copy somewhere and stick them on a board so people can work through themselves. I don't know, but it would be worth trying to do it. But anyway, I hope that the rest of your day is good. Are you doing something good tonight?
We'll print the papers and give them to the study groups.
That would be fantastic. Sorry, Dan, what did you say?
I was saying that we print and give them in groups.
Okay, good.
Individual, then sometimes they do in groups.
That's brilliant. That's brilliant. Thank you very much. I really wish I was there. You know, today it's very beautiful here. It's really sunny and so on. But it is like, I think today is really warm compared with yesterday. The last week it has been like 4, 3, 2, -2 degrees. Today it is 10. It is summer. Right. See you later, guys.
Then is winter here.
Oh, yeah. I will come to Kenya. I will come and spend the winters in Kenya, I think.
When are you coming?
Fed up of UK.
Come. You're welcome.
I will. Honestly, I will come one day. I will. I have to Hakuna Matata. I want to see you guys in the flesh. I want to come and meet with you. So I will. Okay? Oh, pink phone.
Okay.
Fatma's got a pink phone. Oh my God. Look at that.
Don't forget to visit.
She is the queen of fashion. Michael is so
also-
disgusted. Michael is so disgusted. He's walked off. He goes, no, I can't do this.
Fatma is also a
Right. I'll see you later, guys.
Don't forget to visit Silver Spring when you come in Kenya.
I will definitely come to see Silver Spring.
You guys
But
are- we
you
are
might
really
not be
waiting
there
for you.
anymore.
When are you coming?
Well, we are hoping next year.
Oh my, I'll be already done my KCSE.
You will be at university, hopefully.
Yeah, I'll be a comrade.
You better be. If you
And
are
we
not
will
at
invite you to
university,
say
I
hello.
will come and get you. I will come and poison you.
Oh my.
Yeah. All right. See you later, guys.
Okay, thank you for the lesson.
It's a
I
pleasure.
really appreciate it.
It's a pleasure. See you.
It was so enjoyable.
You are
Take
not
care.
right.
Good night.
See you and good night.